Welcome to iLecture Online, and in the previous set of examples we talked about light interference. In other words, we have multiple sources. We've talked a lot about a double source system. We have two sources of light, they come together and the path length difference is different, and so when they come together there's either constructive or destructive interference. But when we have a single slit, you say, well, how can you have interference? And the answer is yes, not really. It's something slightly different. It's called diffraction of light, and we see what we call a diffraction pattern. And there's still some sort of interference taking place here, but let me explain how that works. Well, first of all, if light comes together and shines through a very small little slit, you will see a bright spot right directly across from that slit, and that's called the central maximum. So just like with a double slit system, the spot directly across from the double slit, you'll see a central maximum. Here, however, the central maximum is much brighter than the other maximas, we call it, or bright spots alongside either side of the central maximum. Here they are much dimmer with what we call a diffraction pattern. So this is what we would call a diffraction pattern. And how does that form? Well, the best way to think about it is, what causes a dark spot to appear over here with a single slit? Well, again, as light enters a small slit, it goes in all different directions. And the beam does have a finite width to it, so the various portions of the beam actually do some interference with the other portions of the beam. And if we take a look at what would happen over here, if we have a beam shining to this spot right there and a beam shining to this spot, how does that become a dark spot over there? Well, the best way to think about it is that if we divide the beam into two halves right here, and we draw a line perpendicular to the bottom ray right here, and of course if this angle here is theta and we draw a line perpendicular over here, then this angle over here is theta as well. And notice if I take this line right here at the halfway point of the beam, I can say that this ray right here travels farther than the ray at the very top part of the beam. So there's actually does exist a path length difference for various portions of the beam. So I'm not going to concentrate on that little part, and let me make it red so it's easier to see. Right there, I'm looking at this extra distance right there, and that extra distance is equal to half the width of the beam, a over 2 times sine of theta. Because if I look at this little triangle right here, this hypotenuse is actually half the thickness of the beam. And so the extra distance traveled by this ray compared to the one traveled by the ray traveled at the very top of the beam is a over 2 sine theta. And if the extra distance traveled by that ray in the middle of the beam compared to the ray at the very top of the beam equals a half a wavelength, then those two rays will be out of phase by a half a wavelength, and so the very top ray will destructively interfere with the ray right in the middle of the beam. Which means that the ray right below that will also destructively interfere with the ray right below the one in the middle. And the one below that will destructively interfere with the one below that. And you can see that every ray in the top half of the beam has a corresponding ray in the bottom half of the beam that will be exactly half a wavelength out of phase. And so the first half of the beam will completely destructively interfere with the second half of the beam. And when you look at the screen over here, you'll notice you'll see a dark spot. So that's the condition where if a over 2 sine theta equals lambda over 2, you will have the first dark spot on the screen. Okay, now let's find out how far away from the central maximum that will occur. So let's say that distance is y. Let's say that the distance to the screen is L, and let's say that L is equal to 2 meters. Let's say that we're looking for lambda equals to 600 nanometers. How far away from the central maximum will that occur? And so this condition must be true. First of all, we can cancel out the 2's on both sides. Of course, just like before with the double slit, these are very small angles, so we can say that a times the tangent of theta is equal to lambda, and of course the tangent of theta is the same as opposite over adjacent. That would be y over L, so a times y over L equals lambda. Again, I'm looking at this triangle right here. Let me use the blue color, see if the blue works. There it is. I'm looking at this triangle right there. Here's the angle theta, here's the opposite side y, here's the adjacent side L, so the tangent of theta is y over L. And that's where that analogy comes from. And then if we solve that for y, we can say that y is equal to lambda times L over a being of course the width of the slit, and let's say that a is equal to, how about 1/10 of a millimeter, 0.0001 millimeter. Oh, that should be meters, which is equal to 0.1 millimeter. So just for example, let's assume that the slit is about that width, and we plug the numbers in. We have y is equal to the wavelength of 600 nanometers, 600 times 10 to the minus 9 meters. L is the distance to the screen, which was 2 meters. And then we have A, which is the thickness of, or the width of the slit, which is 0.0001 meter. And this, so the distance to the first dark spot in this diffraction pattern is, okay, times 2 divided by 0.0001 equals, and it looks like, oh, that didn't come out right. Let me try it again. 600 e to the 9 minus times 2 divided by 0.0001 equals, that's better, and that would be 0.012 meters, which y is equal to 1.2 centimeters, or 12 millimeters, so about that much. So the first dark spot would occur 1.2 centimeters away from the central maximum. All right, then how far would it be to the first maximum? How do you figure that out? Well, for that, we have to look at a point slightly higher than before, so I'm going to make that drawing here on the side. So now let's look for the first maximum. So this is the central max. And now we're looking for the first max, or the first bright spot on the side of the central max, and we're looking for y is equal to question mark. We'll use all the same numbers, but how do you find that spot now? So now we're looking a little bit higher up on the screen. The angle is now a little bit bigger, theta is now bigger. What we're going to do now is we're going to divide the beam into 3 equal sections, 1, 2, and 3. We draw a line straight across, and now we're interested in, let me grab my red pen here, interested in this extra distance right there. We're looking at this extra distance. And what is that equal to? Well, notice that it's only 1/3 into the beam. So the hypotenuse of that little triangle here would be a over 3. And so the extra distance traveled would be a over 3 times the sine of theta. Now, why did it just take 1/3 of the beam? Well, I'm looking a little bit higher up on the screen. The angle is a little bit bigger. If I now assume that this top ray right here is a half a wavelength out of phase with the one that's 1/3 way into the beam, when they both then arrive on this side right there, they will destructively interfere with each other. You say, well, wait a minute, aren't you looking for a maximum, a bright spot, then why are you looking for destructive interference? But notice I'm only taking 1/3 of the beam, canceling out the next third of the beam. So if this ray is a half a wavelength out of phase with the next one, and the one right below it is out of phase with the next one, and so forth, then you can see that the first 1/3 of the beam cancels out the second third of the beam, so that these 2/3 are canceled out, which leaves the last 1/3 of the beam able to get through and form a bright spot. But since it's only 1/3 of the beam, you'll have a bright spot that's not nearly as bright as the central maximum. And that's what we had learned in the previous section. It'll only be about 1/90 intensity, but that's for a later session. At least you can see that this portion of the beam does make it through and does form a bright spot. So again, the condition is that the extra distance traveled by the top ray of the beam cancels out the ray that's 1/3 into the beam. That means that the extra distance traveled therefore must equal lambda over 2. So again, we use the same lambda over 2 to find dark spot as well as bright spot. We just look for different portions of the beam canceling each other out. So when we do that, we can say set these two equal to each other. We can say that a over 3 sine theta equals lambda over 2. And sine of theta can be written as a over 3 tangent of theta is equal to lambda over 2. And again, the tangent of theta is equal to the opposite over the adjacent. So that would be a over 3 times y over L equals lambda over 2. And on solving this for y, we can say that y is equal to 3 lambda L over 2a. And when we plug in those numbers, so we can plug in the same numbers we had before, so 3 times 600 times 10 to the minus 9 times 2 meters divided by 2 times the thickness, 0.0001. That's the width. Oh, that's a very tiny little 1 there. There we go. Divided by 2 times 3, divided by 2 times 3 equals, and we get 1.8 centimeters. So if the first dark spot is found at 1.2 centimeters, the first bright spot is found at 1.8 centimeters. So know that it's not a linear relationship here. Now, how do you find the second dark spot? Well, the second dark spot will be found by raising the beam a little bit higher. Here's the slit, here's the screen, raise the beam a little bit higher to find the second dark spot. And what we do there is, instead of dividing the beam into 3 equal parts, we're now going to divide the beam into 4 equal parts. And what we can say is that the ray of the top of the beam can cancel out the ray that's 1/4 into the beam here if, and again, we take that little distance right there, that extra distance over here, and that extra distance now is equal to a over 4 sine theta. And if that destructively interferes with this beam right there, you can see that the first quarter cancels out the second quarter, the third quarter cancels out the first quarter, and none of the light gets through, and you'll see a dark spot there. So the condition is that the extra distance traveled here, which is equal to a over 4 sine theta, must equal lambda over 2. And therefore you can say that a over 4 times the tangent of theta equals lambda over 2, or a over 4 times y over L equals lambda over 2, and then you solve it for y. And then if you do that, you'll get that y is equal to 2.4 centimeters. And then finally, how do you find the second max, the second bright spot? So now you're going to angle the beam up even a little bit more. And I don't have a lot of room here, but bear with me. Here's the open slit. Here's the screen. Angle the beam even more. And what you're going to do now is you're going to divide the beam into 5 equal sections in such a way that the first 1/5 cancels out the second 1/5, the third 1/5 cancels out the fourth 1/5, but then you have the last portion of the beam, the last 1/5 of the beam that makes it through and forms a bright spot that then becomes the second maximum. And so there, in that case, you're going to say that the extra distance traveled by the very top portion of the beam will be a half a wavelength out of phase by the beam that is 1/5, or the ray that's 1/5 into the beam. So extra distance traveled is equal to a over 5 sine theta, and you set that also equal to lambda over 2, and again, solve that for y. So you can see the pattern here. To find the center maximum, of course, there's no angle. You go straight across. To find the first dark spot, you set the extra distance traveled equal to a over 2. That is the first dark spot. To find the first bright spot, you set the extra distance traveled equal to a over 3 sine theta, and set equal to lambda over 2. To find the second dark spot, that's right here. Second dark spot right here. I lost it for a moment. It's getting kind of complicated here. So to find the second dark spot, you set extra distance traveled equal to a over 4 sine theta. And finally, to find the second bright spot, you set the extra distance traveled equal to a over 5 sine theta. And I think you can see the pattern. A over 2 sine theta, first dark spot. A over 3 sine theta, first bright spot. A over 4 sine theta, second dark spot. A over 5 sine theta, second bright spot. A over 6 sine theta, third dark spot. A over 7 sine theta, third bright spot, and so forth. Every time you set it equal to lambda over 2, and you'll find the fringes caused by the diffraction pattern of light through a single slit. And that is how you do that.